Okay, so it's our pleasure today to have Wietze Koops, who will give a presentation on the recursive small step multi-agent A-star algorithm. And we'll get rid of the window that is copying the rest. Okay, good. Over to you, Wietze. Yes, please take it away.
Thank you. So I will talk about recursive small step multi-agent A-star, which is an exact solver for Dec-POMDPs. So yeah, what is a Dec-POMDP? It is a model-to-model, like decentralized multi-agent decision making in a stochastic environment, which is also partially observable. And this is a model that's quite used a lot in reinforcement learning, to model multi-agent settings. We'll tell in a moment more about how this is actually defined. The aim of the research, what this talk is about, is to make exact finite horizon Dec-POMDP solving more scalable. And applications of these Dec-POMDPs include multi-robot coordination and sensor networks. So there are like multiple sensors that are trying to survey a whole area, and they need to decide where to look when something is happening. This exact finite horizon Dec-POMDP solving is a next hard problem. In that sense, also, if you're interested in combinatorial optimization, then of course we have a lot of NP-hard problems, but we know that we can actually solve them typically much better than the exponential complexity suggests. Well, it's also the case here by exploiting structure and symmetry. We can do better than what the double exponential complexity in this case would suggest. So this talk is based on the HKI paper of this year, and I'll introduce the models in more detail. So we'll start with a Markov decision process. So we have a finite state machine. We have probabilistic transitions, and in each state there are multiple actions available. Depending on which action you choose, you get different probability distributions over the next state. And also each action has an immediate reward based on both the action you take and the state you're in. And the goal is to maximize expected reward over, let's say over a finite horizon, or you can also do it over an infinite horizon with discounting, for example. And examples of such NDPs include robot navigation, where the states are the cells of the grid, and then maybe so the state tells you where the robot is, and the robot wants to go from A to B. You have machine maintenance, where you have a machine and there are like several deterioration states. So you have a state that says that the machine is still completely good. You have a state that says that the machine is completely broken down, and you have some states in between that tell you about the state of the machine. And then you have to decide whether you want to maintain it or whether you want to risk that actually the next stage it will completely break down. You have complete failure of your machine that will give you a larger cost than if you would just maintain it before it breaks completely down. So here we also have a schematic representation of the MDP. So we proceed in stages. Every stage the agent chooses an action. This action causes a state transition in the environment, and the agent receives a reward and also is informed of the new state. And this then proceeds for either for a fixed finite horizon, so for a fixed number of stages, or could also be for an infinite horizon. Now we move to partially observable MDPs. So now the state is no longer directly observable for the agent. So this is the part that changes in the model. After each action, there is an observation. From this observation, you can infer a belief about the state. So maybe some observations make some states more likely. Maybe some of them can only happen in certain states. But in general, the agent will not really know the state. And we also observe that we also assume that they don't observe the reward while sort of executing the policy, because that could give them additional information about the state that we don't actually want to reveal. So the observation is the only thing they learn, and in the end they learn how much reward they accumulated over all the stages together, but only after they have executed their whole policy. So in terms of the two examples I just gave, in the robot navigation, maybe there is a maze. The robot cannot see exactly in which cell in the maze he is. He can just see how many walls he can see from this cell. And that's then his observation, the number of walls. And then he knows that, okay, some cells are impossible because they have another number of walls, but he doesn't know exactly in which cell he is. well, maybe in the machine deterioration example, we don't know in which of these intermediate stages of deterioration the machine is. We only know that if we choose some inspect action that tells us this. But otherwise, you only know if the machine, okay, we observe, of course, observed if it's completely failed, but anything else is not observable unless we choose an action which says inspect the machine, which of course has some cost. Yeah. And of course, now this policy already becomes more complicated because in the MDP example, policy is just a map from states to actions and also maybe the number of stages you still have left. But now it has to be a map from observation histories to actions or from state beliefs over to actions. So this policy becomes more complicated. Now we go to decentralized POMDPs. So that means that we add multiple agents. And decentralized means that they cannot communicate during while executing the policy. They still have a common goal, so like all the agents are working together to maximize the rewards. Yeah, but so they have to locally select actions and only receive local observations, which might be different. So how execution of such a policy works is that all of the agents select a local action. These actions are combined and cause a state transition in the environment. And each of the agents get their local observations. And then based on these local observations, they again select an action, can cause a state transition, and then they can get observations. So that's how a Dec-POMDP works. But the important thing is that they cannot communicate while executing the policy. Okay, so like I said, the aim of this research was to make exact finite horizon Dec-POMDP solving more scalable. And our approach built on multi-agent A star. But we have two new ideas, which I'll of course explain in more detail. So the first is that we do a small step multi-agent A star. So in A star we have such a search tree, and all the original approaches have a double exponential outdegree in the search tree. We reduce it to constant. The cost is that the height of the search tree is increased from linear to exponential. And secondly, we propose some new ways to work with the recursive Dec-POMDP heuristic, which is tighter and allows for more pruning in the tree than the approaches that we used earlier. Okay, so what's an example of such a Dec-POMDP problem? Well, this is sort of the classical example, the deck tiger problem. So we have two rooms, and each room has doors for each agent. In one of the rooms there is a dangerous tiger, and in the other room there is a very there's a treasure. And but the agents cannot see from the outside which of the rooms contains the tiger and which of the rooms contains the treasure. So these are the two states. The tiger could be in the left room or in the right room. And there are three actions which are open left, open right, and listen. So that just means that the agents are going to either open one of the doors, and that's also for the top agent, this is the right door. Or they can listen, and then they can get some information about where the tiger is. So yeah, I mean, if they listen, then they might hear the tiger in the left room, they might hear the tiger in the right room, but this is only correct with the 85% probability. And it is correct for both agents independently of each other. And also over the stages, it's independent.
So that you can get observation errors in both directions? Like
yes.
15% you can hear the money roar.
Well, I mean, it's just that you think that you hear it on the right. So let's say in each case you hear something, yeah. But you might just be mistaken about where you hear it on the right or on the left.
Okay.
Yeah. So, but there can be observation errors in both directions.
Yes.
In particular, it's possible that you just open the wrong door and then you get a huge penalty. Of course, you do want to open the door with treasure, that gives you a reward, and also waiting and listening also gives you a smaller penalty. Also, opening a door resets the problem. So over finite horizon, you can try to do this multiple times. You want to get the treasure multiple times while holding the tiger every time. Yeah, so opening a door resets the problem, so then they might switch secretly without.
So we're going to play this multiple times.
Yeah, so we played over a finite horizon. So maybe beforehand we agree we'll play this for 9 stages, and then I mean maybe the agents decide to open a door at stage 3, and then it will reset. And then so then they can maybe again open it at stage 6 and again at stage 9.
Do we know the time horizon?
Yeah, the time horizon is given up front. Yeah, so but the agents do not know of each other whether they open the door, so they particularly don't know whether the problem was reset, so they don't know if their current observation is still valid or not. That's this no communication thing from Dec-POMDPs. So the only thing that they know is like the policy, so they don't know the time horizon and they know the policy that they agreed upon beforehand. So this policy that maps observation histories to actions. So here is an example for Horizon 3. So we have, I mean, we would have one of these for both agents, but in this type of problem, actually, both of the agents are going to do the same thing. So here I just did the policy for agent 1. If we have the empty observation history, which, I mean, just in the beginning, we don't have any observations yet. Yeah, of course, I'm not going to risk opening a door. I'm going to listen, get some information. Then I have an observation, either here right or here left. Well, if that's not actually not enough information to already risk opening the door, so I'm going to listen again. And then if I got twice the same observation, if I hear the tiger on the right twice, then I'm going to open the left door. And if I got mixed observations, I'm just going to have to listen again. And if I heard it on the left twice, I'm going to open the right door. So this is how such a policy looks like. And I mean, if we increase the horizon, then we have all the observation histories here. So that's why such a policy is typically like an exponentially large object in the horizon. That's also why it's double exponential to search over them. At least if you do it naively, but yeah, apparently complexity tells us that you cannot really do better. Okay, so I mean, our approach is an A-star algorithm, so I'll just briefly tell you something about what A-star is in general. With a simpler example, we have a shortest path problem in the graph, and let's just say that the graph is embedded in the Euclidean plane, so that we have coordinates for the points that will help us to get heuristics. So we call the source S and destination T. And now A-star, well, it works a bit similar to Dijkstra, but we use some heuristic function which might be different from choosing the nearest vertex from the source. So we're going to choose the each time we're going to expand the heuristic with the lowest heuristic value. And then we're going to add all successors of that heuristic to our queue with open vertices, so to the frontier. Yeah, like I said, it works similar to Dijkstra, where we just pick the closest vertex to the source. So then our heuristic function is just the distance from the source to that vertex. Yeah, so when does A-star actually find the shortest path? Well, that's the case if the heuristic is under approximation. So the heuristic for vertex V has to be smaller or equal to the shortest route via V. And that's exactly the distance from S to V, but the distance of V to T. And also the heuristic has to be exact on sort of once I reach. Yeah, I mean, in this case, I only have one destination. But also, if I have multiple destinations that I might want to reach, it has to be exact on all these sort of terminal nodes when I found the whole route. Well, if this is the case, we call the heuristic admissible. And why is then A-star exact? Well, I mean, what's invariant in this algorithm is that every route passes a vertex on the frontier. That's also the case in Dijkstra, and here that doesn't change. So every route from S to T passes a node W that's currently in the frontier. At the moment that I stop once I pick T out of the frontier. Well, I know at that point that is the heuristic value that corresponds to T is the actual length of the route. And I also know that I always take the value with the lowest heuristic. So for all the other nodes W that are in the frontier, well, they have a larger or equal heuristic value because I choose the lowest heuristic value. And then I also know that that's at least the shortest path that goes via W. And since every path has to go via such a W, yeah, I mean, the route that we found here has to be a shortest route. yeah, so if you want to do this for shortest path finding, then I mean, like you can use Dijkstra's, but you can refine it because we're in the plane. You can sort of add the distance as the crow flies to the distance, and then that's going to be an under approximation for the actual distance if you have to follow the axis of the graph. And yeah, I mean that typically finds the paths faster than just doing Dijkstra. Yeah, so here with the shortest path finding, we're doing a minimization problem. So then the heuristic Q must be an under approximation, but the rest of the time we will do without maximization, and then sort of everything turns around. So then actually the heuristic must be an over approximation for our algorithm to be exact. So a heuristic is an over approximation for the actual value that sort of goes via that vertex, or yeah, that's sort of an extension from, like you can also see this graph as a sort of search tree where the labels are not vertices but actually routes from the source to the vertex. Except that you're also optimized that you're not going to add multiple vertices like with different routes. But yeah. So here's also another just more numerical example. Suppose that we have this tree. So all the leaves correspond to sort of final options. So they would correspond to routes, for example, or they will correspond to fully specified policies in what we'll see next. Yeah, so here I am still doing, okay, so here I already turned it on to maximization. So I want to find the maximal leaf, which will correspond to the maximal policy that we want to find. So that is now at the 5. And above there are some heuristic values. The idea is that we don't want to expand them all. We're going to expand them step by step. So this is how the book would look if we expand it all, but we don't want to do that. So we start at the end 3. Now we're going to expand the node. In principle, we could also compute the heuristic value for the root, but I mean, we're going to expand it anyway as the first thing. So why would we do that? So now we expanded the root, and now we have computed heuristic values for the 2 successors of the root. So they're 9 and 7. And I'm going to take the highest heuristic value because I'm doing maximization. So I'm going to expand to 9. And then I find, okay, here I have 1 and here I have an 8. But then the 8 is the highest one. So then I find successors 5 and 2. So now I know that there is a policy which has value 5, but I cannot prove yet that it's optimal because, I mean, maybe this 7 has some successor that has value 7 over here. So now I also need to expand to 7. Then I get the 6 and the 3. Okay, so I also still need to expand to 6. And then I see, okay, here are the leaves actually 3 and 3. So I don't do, I mean, those are worse, and here I have 1 and 3, so I don't need to expand them further. So this sort of partial expansion of the tree shows that 5 is indeed the best, because everything that's below the unexpanded nodes is going to be, well, at least as most as good as what's in this heuristic value, and those heuristic values are already large, already smaller than the 5 that we found. That's how a star search works. So now I have multi-agent A star, where I work over a finite horizon H, and the policy specifies an action for each agent for each local observation history of t from 0 to h minus 1. So it specifies an action that the agents take in the beginning, then the agents get a observation, then it specifies for each of the possible observations that they got an action, then they get another observation, and for each pair of observations they specifies an action, etc., up to the final stage where they have h minus 1 observations, and it specifies an action for each of these observation histories. So that's the policy. And multi-agent A star works with a star search tree of, well, partially specified policies. And like I said, the node expansion is guided by heuristic. And here we have a partial search tree of the Deck-Tiger problem. So here in the root node, we have sort of the empty policy. And now what multi-agent A star does, it specifies an action for each observation history of length 0. So for both agent 1 and agent 2, it's going to tell what they're going to do at the empty observation history. Well, there are 3 possible actions, so there are 9 possible partial policies here. And then from stage 1 into 2, multi-agent A star chooses an action for each observation history of length 1. Well, there are 2 of them for agent 1, 2 of them for agent 2, so 4 in total. So we have here an outdegree of 3 to the power of 4. yeah, so this continues in general. We in, let's say, stage T, we add an action for all agents for all length T local observation histories. And this leads to a double exponential outdegree because the number of length T local observation histories are exponential in T. And then I have to consider the number of ways to assign actions to that. That's double exponential in T. And it's the number of agents. This A star is the number of maximum number of actions, and O star is the maximum number of observations. Yeah, so this is what is known, and there are a few requirements of this, leading to generalized multi-agent A star with incremental clustering and expansion. So what incremental clustering does, it clusters together local observation histories for which you can already prove beforehand that the action is taking the same action is probably optimal. So for this, we at least need to know that sort of the distribution. So we have some observation. I have two observation histories. At least the distributions over the state has to be the same. So based on these observation histories, we have some belief over what the state could be, which is the probability for every state. Those have to be the same. But in addition, also you need to know what the other agents are doing, or at least your beliefs over what the other agents are doing are going to do have to be the same. In principle, this becomes quite a hard problem because you have to know something about what the other agents are doing, but you also have to know something about the other agents are thinking that you're going to do, etc. So this becomes quite a complicated knowledge problem. What you can do is say we can cluster together two observation histories if your belief over the state and the observation histories of the other agents are the same. So that's the criterion. Yeah, what it says here. So the same joint belief over states and local observation histories of other agents. For example, in Dec-Tiger, you can see that the order of the observations doesn't really matter as long as you know that there has not been a reset in between. So if you know that in no case any of the agents is going to open the door, then you know that it doesn't reset, and then the order of observation doesn't matter, and you can cluster them together. That's incremental clustering that also works together with the new algorithm that I'm going to explain later. Then we also have incremental expansion, which tries to alleviate this double exponential outdegree by not adding all of them at once, but sort of finding another way of finding the best successor. And then if that one doesn't lead to a fully specified policy, then we try the next best successor, etc. So you have to sort of have a way to incrementally deliver the next successor of a particular node. So the main problems for this is that still, despite the clustering, which sort of reduces the outdegree a bit, still the outdegree is typically double exponential, and then incremental expansion also doesn't really help enough to sort of reduce that to a manageable amount. You need to do a lot of precomputation for this method, and also the heuristics are typically not tight enough to limit the node expansion. So typically you still need to expand many nodes to get to a fully specified policy and prove that this is indeed the. So our contribution is small step multi-agent A star, and it says, okay, we don't want this double exponential outdegree. Instead, we're going to just assign one action at a time, and then the outdegree is the number of actions. So first, we're going to assign an action for the empty local observation history for agent 1. So what agent 1 is going to do in the first, like in the stage 0 before there are any observations, then for agent 2. And then for each of the possible local observation histories, or observations in this case, of agent 1 and 2, we're going to assign actions, again, one by one. So that reduces the outdegree to a constant, but it increases the height of the tree to exponential, because now we have all these exponentially many local observation histories here in the tree. But the good thing is that if the heuristic would be very good, then you just walk down completely and then you find a solution in exponential time. Which is better than, I mean, here, even if the heuristic would be perfect, it always takes double exponential time, because you always have in the bottom layer an expansion which has this double exponential outdegree. Okay, so when so still set multi-A star, when expanding a node, you add an action for only one local observation for one agent, and that means that partial policies at level L in this tree are going to specify actions for L local observation histories in total. So that's how this tree looks like. And then the second part of the improvements is about these heuristics that we use to guide the A-star search. So again, a admissible heuristic, because we're maximizing, has to be an over-approximation. If we have such a partial policy 5, this call out here represents the partial policy that does listen in the first stage for both agents. Then we look at all the partial policies that do the same thing in everything that's already specified. And we look at the best policy there. Yeah, the heuristic has to be an upper bound for that. So let's look what heuristics we can choose. Just in general, like I said, the upper bound has to be, the heuristic has to be an upper bound for the value of the best descendant. And the current approaches are, well, there are 4. So you have the MDP heuristic, which kind of says, okay, I'm just going to pretend that the problem is an MDP from a particular point onwards, like from the point I specify my policy up to a particular point, and from that point onwards, I'm going to pretend it's an MDP. Just like in the A-star, you can pretend from some point onwards that you can just take a straight line. I mean, this is an upper bound because, of course, the agents can access the state information and can collaborate, and they can do much better. Similarly, you can do this with the POMDP, so then you don't reveal the state information, and you do reveal the joint observations, which automatically also means that the agents are sort of allowed to communicate because they have the same information. They can just reason about what would be best. Then we have QBG, which is called observation games, how it's computed, which is communication with a 1-step delay. So that means that all the agents still get their own local observations, and they get the joint observations from one stage earlier. And finally, you have Q-Dec-POMDP, which means that we reinterpret the problem as a Dec-POMDP for all next stages. So then you share the joint observations once, but not anymore in stages after that. And then if you share the joint observations from the past, then the agents can compute a new joint belief that they have together. And that sort of counts as restarting the Dec-POMDP, because then they again have the same initial belief. Yeah, depending on which joint observations were there. So what are the problems for this? Well, so this QMDP, QPOMDP, and QBG are in sort of increasing order of tightness, but even QBG is generally not tight because you still reveal a lot of joint observations eventually. And also there is an expensive precomputation for QBG, which includes this stored exponentially number of observations and number of agents. And Q-Dec-POMDP is just too expensive to compute or pre-compute, especially for large outdegrees, because you need to compute some type of heuristic for every node that you're expanding. And this Dec-POMDP heuristic is quite expensive to compute. But that changes once you have this small step search tree. So basically, having this small step search tree allows this approach to become fruitful again. Whereas before it just wouldn't work because it's just too expensive to compute as heuristic. So how do we define this recursive heuristic? Well, for that it's useful to first look at the sort of generalized policy, where the policies are based on joint observations of all agents. So we say that, yeah, the policy of the agents, each of the agents has their own local policy, but they are allowed to use all the observations. And then if we look at the Dec-POMDP optimization problem, then we say, actually, it's a constraint optimization problem over these generalized policies, where the constraints exactly tell me that I'm not allowed to use the joint observations of other agents. So basically say, if I have 2 joint observations and they only differ in observations of other agents, then I have to take the same action, because actually I cannot distinguish them. Another idea is I have this constraint optimization problem. If I relax constraints in that, or relax constraints in the maximization problem, I get an upper bound, so that gives me a missable heuristic. Yeah, I mean, I just don't only need to heuristic for the whole problem, I also need a heuristic for each partial policy. But then I just maximize over the extension of the partial policy, so all the policies that agree with this phi up to the point where phi specifies this. And now, of course, also the question is, I mean, I can relax constraints, but why does that make the problem easier? Well, if I relax the constraints, let's say that the agents cannot use the first D joint observations, then actually sort of you can recompute the joint belief that the agents have after these stages. And then you have a new horizon H minus D that could be from that stage onwards. So then you can solve this recursively. Okay, but it's quite a happy recursion because you have to do this for all the observation histories, which can be exponentially many. How do we make it more scalable? Well, we can terminate early in A-star search and still get an upper bound. Because, I mean, the highest value of an open node is always going to be an upper bound for the optimal solution in A-star search. So what we can do is just return the highest heuristic value after m steps of running this A-star search, and that's still going to be an upper bound. Yeah, I mean, it's going to be an upper bound for an upper bound, but still this turns out to be usually better than approaches that reveal more information. Another thing that makes this more scalable compared to other approaches is that you don't need to precompute this. You can just say, I need some heuristic at this point in the tree, and then you run, you run the nested loop of the solver to get the heuristic based on this lower horizon Dec-POMDP by this QBG approach, dealing with a precomputation. Okay, so then we turn to the results. So here we have the state-of-the-art solver GMAA star ICE. And here I computed results using the same heuristic for both solvers. So both the QMDP heuristic, which is generally, I mean, it's not tight at all. So generally you don't get very good results for this with this heuristic. But what we see here, I mean, what GMAA star ICE has and what small step multi-HA star doesn't have is incremental expansion. Here we see that the small step approach always at least works as well as incremental expansion. Of course, incremental expansion you don't really need anymore with the lower, with this low outdegree. So, but then if we also add the new heuristics, and then also, of course, allow for GMAA star ICE to use different heuristics. So essentially, all the heuristics that have been implemented, MDP and two implementations of QBG. Dec-POMDP is sort of in between here and doesn't give better results than either of them. Then we see that mainly on Dec-Tiger, mask rovers, and recycling robots, our solver really works much better. Maybe also one thing to notice is that here the firefighting problem, before this with the MDP heuristic, this was at least 2000. Now it jumped back to 6. So it's because for this problem, this actually horizon 5 is the hardest horizon for this problem. And here it sort of gets stuck in recursion trying to solve hard horizon 5 problems, whereas you can avoid that with the MDP heuristic. But for all the other problems, using these recursive heuristics works well, as good or typically better than using the MDP heuristic.
I have a very naive question. What does it mean to solve a horizon? I mean, are we computing optimal strategies here, or what?
Yeah, so solve a horizon means that we compute an optimal policy for that horizon. And
the optimality of that policy does not depend on the heuristics or anything, like it is.
No, so as long as the heuristic is admissible, so a guaranteed over approximation, then the proof guarantees that the policy that the algorithm outputs is a best policy.
Okay.
Yeah, so you can also run it with heuristics that are not admissible, but then you get typically a worse policy, or at least you don't get a guarantee that you have the best policy.
So that means that in particular, we can use your solver to output an explicit strategy for two collaborating agents to play 12 rounds of this decision tiger.
Yes. Yes, and then this policy is already somewhat large because so you use clustering. RS-MAA star can also use clustering, but still you sort of have clustered observation histories of length 11, and there are a couple of hundred of them. Yeah.
Is there any structuring, do you think, that you can see, or you just
depends on the problem? So for Dec-Tiger, there's sort of a periodicity. So if your horizon is a multiple of 3, then you just want to open the door every 3 stages. If it's 1 or 2 modulo 3, then you just add one more observation to one of these things, or two more observations, because it's 2 model out 3. Yeah, and then for some others, for some of them it's much more complicated. Also, of course, yeah, some of them. So there's sort of a big division here. They're like their horizons. They're like problems where you can only do a little bit better than. Well, okay, maybe it's a little bit better than brute force search is a strong word, but we're still searching over on the order of 10 to the 200 policies or something. But right, where you have some problems where you only reach up to, let's say, around 10, and you have these few problems where you can reach up to 2000. So the big difference between these two classes of problems is that the problems where you can reach up to 2000 are problems where the clustering size is constant. So where you can really already prove beforehand that you only need to remember the last observation, essentially. That's what all of these problems are. Or even in the case of the broadcast channel and the firefighting, you don't need to remember anything from a certain point. Like for the broadcast channel, you don't need to remember anything. For the firefighting, you don't need to remember anything as soon as you know for sure that the fires have been extinguished, which happens after Horizon 6 in the optimal policy. So that's sort of the big division between the hard problems where clustering doesn't. I mean, it reduces the number of clustered observation histories a little bit, but it's still typically growing exponential, just with a lower base than without clustering. And the problems where clustering works really well. Okay, so we can go to the conclusion. So recursive small step multi-A star solves two major scalability concerns. Actually, this is right. Yeah, two major scalability concerns, maybe even 3 compared to GMA star ICE. So we have an on-the-fly heuristic computation instead of an expensive precomputation. We have a constant outdegree instead of an exponential outdegree in our search tree, and also we actually have tighter heuristics which make the which limits the number of nodes that you need to expand. You can also see that as a scalability concern that you solve. And there are significant improvements on several standard benchmarks because of this. Of course, there are also some remaining scalability concerns. So firstly, the recursive heuristic can be quite expensive to compute, even with this like early termination of the heuristic. The number of clustered observations is often still exponential. I mean, that you can only do something about by giving up exactness and say, okay, I'm going to do some lossy clustering and try to find a good policy with this lossy clustering, or maybe even an optimal policy, given that you only want to keep that many observations in memory. But that's for future work. Thank you.
Thank you. Any questions?
Yeah, maybe on the 22nd slide where you talk about early termination. Like, how do you choose that constant m? Is it
it's sort of a parameter tuning, and also it's
or do you do it automatically or hand tune it each time?
hand tune it is not well. So what I just sort of hope that there is a value which is reasonable for many problems. At least if you're like sort of other problems have roughly the same size, like maybe a couple of tens to a couple of hundreds of states and maybe 5, 6 observations per agent, 5, 6 actions per agent, something around this stage. And then it turns out that 200 works well for most problems. Also, yeah, I mean, if you increase m, it doesn't. The running time increases a little bit. If you decrease m, then in the worst case, it sort of explodes because your heuristic is not tight enough anymore. Then you explode way more nodes. So we found that 200 is a good value for actually other problems to look at. Also, if for some problems you really want a different heuristic. So yeah, here are the 3 heuristics that the end generated these results. The first value describes the m, and the second value describes the depth d, where d is infinity means that sort of we keep increasing the depth while the search progresses. And for these easy problems, sometimes you really want the 25, otherwise you typically run either out of memory or out of time before you reach these really high horizons. But even there, 200 still does fine. Just maybe reach 500 or horizon 500 or horizon 1000 instead of 2000.
Okay.
Other questions? Comments? How, I mean, when you're looking at different solvers for different type of combinatorial problems, it's interesting to understand what the level of, what should I say, maturity is. Is this like used for real world problems somewhere, or is this more like, you know, development on academic sort of toy benchmarks or somewhere in between?
So there, this GUA star IC has a proper toolbox that actually people do use. But I mean, these programs are still quite small, and the horizon you can solve is also not that large. So for real world problems, this is still, real world problems are still too large to solve up to any reasonable horizon. What it can be used for is sort of in development of approximate techniques, and there people do use it to compare their approximate solver, their reinforcement learner to the exact values.
So how would this work? You have some kind of heuristic approach and you run it on semi-long horizons and compare it to exact to get a sense of how well it's doing, or?
Yes, so you would compare it to sort of the highest horizon that you can solve exactly, and if there the value is good, then that's, I mean, then you have some hope that also for larger horizons the value will be good.
Yeah.
Because on the other hand, like the other way around, if your solver is already doing poorly on low horizons, then probably it's also doing poorly on high horizons. But there is at the moment there's not really an alternative for doing this. That there's also not really a good upper bound finder or something, or that you would have to do with similar techniques.
And do you know these heuristic solvers? Or maybe you said a little bit about this before. Like, where would you use this in practice? Just curious.
So I mean, you just have a setting where agents are interacting. So let's say robots, for example, and they cannot communicate either because they're like small cheap robots that don't have a communication unit because you want to use them. You have many of them or something like this, or also communication can cost relatively a lot of battery power, so that's why you don't want to do it, or you want at least don't do it by default and put a cost if you do want to communicate, because you can also model that there is like an action. Okay, communicate, but there's some cost. Or this other example that I gave was a sensor network, where you have sort of sensors that are independently like trying to survey some area, and then maybe one of the sensors detects something somewhere, and another sensor also detects maybe the same thing. Then not all the sensors that detect that should like focus their full attention on that point and then leave like the rest uncovered. So there should be some kind of policy that says, okay, if I detect something, then there's going to be a little bit more focus on that point, but not like completely leaving everything else unsurveyed. There are also some applications of Dec-POMDPs into maintenance of machines, where, for example, you have if you have a car with like you have one spare wheel, right? So you need to have 4 out of 5 wheels working. And if maybe a wheel is too simple, but in general, you can imagine that you have a machine where you need to have 4 out of 5 components working for the machine to be working. And that you can also model as a 5-agent Dec-POMDP, where sort of there's the rewired models where there are at least 4 or 5 things are working and some maintenance actions. There you can also use this. In general, I mean, applications, they're a little bit sparse, especially because, I mean, there are just not that many good algorithms yet to solve this, but hopefully there's going to be change in this.
Fair enough. Okay, so let's thank Wietze again.
we go. Good. So we're back for the second technical half. If we can get it seems to work. Good. So it's over to you again, please.
Yes. So here is some more details about how we formula define a Dec-POMDP. So maybe that also helps a little bit in understanding the model. So we have a set of agents, we have a finite set of states, we have a set of joint actions, which are sort of decomposed as tuples of local actions AI. We have a transition function. What does the transition function do? Well, it takes the current state, it takes the joint action of the agents, and it maps that to a distribution over the next state. So it tells us what the probability is of a particular next state given well, the old state and the action. Then we have joint observations, which are again decomposed as tuples of local observations. And the observation function tells us, well, we had an action, we have a new state, so we already have changed the state according to the transition function. The observation function tells me a probability distribution over the observations that we can have. We have a reward function, which depends on the state and on the action. So the old state, which you can, yeah, I mean, if you have rewards that depend on the new state, you can just take the expectation of it and get them over the old state. We have an initial belief, which tells us well, what all of the agents think that the initial the probability distribution of what the initial state is, and we have the horizon.
So the state is the global state, like with all the information of all agents, like
no, so the state is this sort of hidden state of the model.
The state is reality.
The state is reality. Yeah.
Okay.
So
But which we
like
will only
everything.
partially observe.
yes. So for example, if we have a grid where there are multiple robots, then the state is the exact location of each of the agents, but the state does not include like information about what the observations the agents got, for example. It's just the state of the model.
But the transition function, was there some kind of randomization in this? Because you said it's a distribution?
Yes, so it's not
So like,
deterministic in what is the next state if you are in even if you know what state you are now, it's still not deterministic what state you will be in next if you take an action.
okay,
So-
and this is modeling.
Well, for example, you are in a grid when the floor is slippery, so maybe you slip to a different cell than you intended to go to.
Okay.
Or yeah, for example, it can also model this reset action. So the backtracker problem, what it is modeling is that once agents open a door, then the next state will be reset again, and that's half-half. But yeah, typically this models.
Okay, that makes sense. Yeah.
Yeah, so
Yes, yes.
typically what this in sort of applications, what this would model is that there is some chance of things going wrong. So just, yeah, I mean, many of these problems are navigation problems and just, you don't go the direction.
Yeah, or your Martian rover, like you made all the right choices, but it got stuck on some Martian sand somewhere anyway.
Yes, and then just, I mean, you can do whatever action you want, but the action will remain like, oh, you're stuck.
Yeah, okay.
Or
Just a reinterpretation. You're saying that the reality might be affected by the action of the agents, but the agents themselves might know this or might not know this, but we know this as the modeler.
yes, the modeler, so sort of all these things are known to the modeler.
And what is horizon, by the way?
Horizon is the number of stages for which you
It's just the length of
yeah.
play.
the length of play.
I guess another thing I was like that struck me that seemed to also implicitly happen in some of the things. Like you could imagine that you're playing for a horizon capital H, right? But you somehow just believe that I have limited memory. So although I'm going to play for capital H stages, somehow maybe I only, I don't know, remember lowercase h time steps or something. Like this, is this being done? Does this make sense? Or
Yes, this is being done, but you of course lose your exactness guarantee because you can still look for the best policy that uses a particular amount of memory.
Yeah.
That has maybe been done in the context of modeling a policy as a finite state controller. So you just have a number of, for each agent you have a finite state controller. You just have a number of states of the finite state controller, and based on which state you are, you take an action, and based on your observation and your old state in the finite state controller, you go to a new state in the finite state controller.
Oh.
So that's something you can do. Yes.
Which sort of obviously you're saying that makes it more like easier to compute, but on the other hand, the strategies you might be able to compute are then worse because
Yes.
of your limited memory.
Also, there is some way in which this does not make it easier to compute, because if you have such a finite state controller and you sort of specify a particular transition index, then it has an effect on all the horizons, because we shouldn't have one finite state controller which is independent of the horizon. And that sort of excludes an incremental way of building the finite state controller. Like here we can sort of build the policy in an incremental way. We can first just decide what happens in the first period and then what happens in the second period. With the finite state controller, you can no longer do this. So you might still be in trouble when you do finite state controllers when you're sort of if there are way too many to brute force, then it's still hard to find a way to actually do this smart way with finite state control. Yeah, then we can talk a little bit more about the heuristics. Let's maybe close this so we can see this in the slide. So, like a local policy, so something that actually the agents can use, maps sequences of observations of length at most h-1 to actions, local actions for agent I. And like we said, okay, to model an upper bound for this problem, we can use a generalized policy, which actually moves joint observation histories to local actions. And then we can write the Dec-POMDP optimization problem as a constraint optimization problem of a generalized policy. So here we have, well, this pi gen denotes the set of all generalized policies.
Sorry, a generalized local policy. The joint, but are we somehow assuming now that they still, I mean, are we just mapping each local observation horizon to a local action, or are we somehow assuming that they know about each other now? No.
Yeah, so generalized policy is suddenly assuming that they know about each other, that they get each other's observations. Of course, like so most
Which is not
generalized,
the case.
yes.
Given this information would, for instance, be a way of getting an upper bound, because then you have more information.
Yes. Yeah, so the idea is that I can sort of transform every local policy to a generalized local policy by just saying ignore all the extra information that you got. Mm-hmm. And conversely, I can I can add constraint to my optimization problem and say, oh, actually, so formally your object is a generalized local policy, but actually it represents a local policy because the constraints tell you that it does. Yeah. That's not what I'm doing here. So this is still, I mean, it's a weird way to represent the Dec-POMDP optimization problem, but this is still exactly the same problem. So we say we maximize our generalized policies, so which are just like tuples of generalized local policies for every agent. And here we have the value of that policy corresponding to a specific initial belief that they are given horizon H. So I just include these two arguments because in the recursion you might need to change these. And then this constraint is telling me that actually agents cannot use information that's not their information.
So tau I are the local observations of agent I?
Yes.
Right?
Yeah, so I have two joint observation histories, tau and tau prime. And then I look at the local observation histories corresponding to agent I. If those two are the same, then actually not like this generalized policy has to take the same action on these and on these joint observation histories. Mm-hmm. And it has to hold for all agents for all joint observation histories.
So you're saying without that subjection, without that condition, it's like there is no multiple players. There is just one global player.
Yeah, there's just one player that happens to sort of be decomposed as multiple players. That's still an interesting problem. So all these Dec-POMDPs we're solving actually for 2 agents. It also maybe works for 3 or 4 agents. But if you have more agents, then you need to sort of explicitly like decompose the problem. That's also an interesting strain of research. It's not what I'm doing, but yeah, there are also interesting challenges over there. But if you just do, actually, if you just do this, then it's a POMDP. So it's a multi-agent POMDP, but that is just a POMDP, and you can solve with a POMDP solver, except that, of course, your action space and observation space are going to blow up exponentially in the number of agents.
And this, I guess I should know, but I don't. Like when POMDPs, people also are studying a lot, but are there better like algorithms for?
Yeah, POMDPs are in P space. In particular, there exists, so sort of what makes POMDPs easier is that you have this decoupling, so you can do sort of a recursive, sort of a dynamic programming approach, but you have to do it over the belief state. So maybe I can tell a little bit about this. So first, how do you solve an NDP? So an NDP you can solve in time that's linear in the number in the horizon, quadratic in the number of states, and linear in the number of actions. What you can do is in the last stage, it's easy, because then you just want to take the action that maximizes your reward. You know in which state you are, so you just look at all possible actions to look at their immediate rewards, and that's it. And then for the previous stage, what you do is you say, okay, I again look at all the actions, I look at their immediate reward, and I look at their expected reward over the sort of next stage according to this transition function, and this other value that I computed before.
Kind of dynamic programming.
Yeah, it's a dynamic programming approach. And yeah, you pick up the S squared because potentially for maybe it's even just a factor S. So what do you do is for every so you have to do it for every current state, and for every current state there might be, if you take an action, there might be a distribution of the states for the next state. So that's why for every action state pair in the current horizon, you have sort of many things that you need to compute, or like you need to take the expectation of over the states essentially. So that's why it's number of actions times number of states squared times the horizon. And then if you want to solve a POMDP, what you can do is you make the belief MDP, and this sort of has as the states, it has all the beliefs that you can make up to horizon H, and that just depends on the number of observations that you could have made. So then you can solve. Yeah, I mean this belief MDP has an exponential number of states, but that shows that you can solve the time it's exponential in the horizon. And that's sort of, so in principle, if you look at other policies, then for an NDP, there are exponentially many policies. For a POMDP, there are double exponential policies. But for those two problems, the sort of this dynamic programming approach and this belief NDP plus dynamic programming approach sort of gives you an exponent by doing it more efficiently. But in a Dec-POMDP, that doesn't work, because what is in case of a POMDP, what this sort of is doing is saying what you do for one belief doesn't matter for what you do for another belief. And that's not the case for a POMDP, because what you do for one belief has an effect on what other agents want to do. Right? Maybe you take a dangerous action that only works if the other agents also do particular things, but another agents are going to do that particular things, but also if they don't know for sure that you're going to do that particularly dangerous thing. So then it also, via the other agents, has an effect on what you want to do in the other beliefs. So maybe if you're not so sure that the other agents know what you are doing, you don't want to do one dangerous thing in one belief and another dangerous thing in another belief, and sort of them not being able to adapt to both of these things, or like adapt, like agree beforehand that they're going to help you with that. So in that way, Dec-POMDP is more complicated, because you have interaction between different joint beliefs, different local beliefs, that you need to take into account when creating your policy. Whereas with the POMDP case, with the centralized case, where you can separate these problems and solve them, separately. So that's the big why POMDPs are exponential and Dec-POMDPs are double exponential. Okay. So this is also why this heuristic sort of a mix between a POMDP and a Dec-POMDP. Like I said, I'm sort of exploiting this good property of POMDPs that these problems are independent. So that's actually what's on the next slide. So here we have the Dec-POMDP optimization problem again, same problem as just over here. We denote the prefix of the first D observations of some joint observations with tau by this prefix of tau and D. And now we're going to relax this constraint to include this condition that the prefixes are equal. Which means that if two joint observation histories differ in their initial D joint observations, then I no longer have this constraint. As long as they don't use any joint observations that are beyond the D joint observation.
So if I'm trying to rephrase, you're somehow saying that magically you're allowing communication for the first D rounds, and then you sort of switch off the network, and then you're on your own.
Yes, that's what this heuristic in a sense is doing. And actually, so sort of also, of course, we have this policy 5, which is partially specifying this. So while allowing communication, actually sort of the way this works is that I'm allowing, you should look at this like allowing communication at stage D about everything that happened before stage D. Because everything that sort of was before stage D is already fixed with this policy. At least that's how I choose it, how I choose the D. That's actually, I think that's nice. A few slides further. But I can do this first. So, I mean, then of course, the question is, it's nice to relax some constraints and say, okay, we have an upper bound. Why is this easier to compute? I mean, if I just relax some like arbitrary constraints in here, it will generally probably get harder to compute. But by relaxing these constraints, it becomes easier to compute. And that's exactly because here we sort of have this POMDP property that different, I mean, variables with sort of, if we see these different policies as sort of the variables we want to optimize over, then variables with different prefixes only appear very objective. They're not going to appear together in the constraints because that's exactly what sort of this tells me. If I have this constraint, then these two prefixes were equal. And that means that we can sort of decouple that. We can write the maximization problem over all these variables as a maximization problem over a subset of the variables plus another maximization problem plus another maximization problem. And that's exactly what this is doing. Okay, so first we have to deal with the sort of the reward that's already accumulated before stage D. So that only works if this policy that we specified already specifies the policy up to stage D. And then we have this sum. So we sort of take a weighted sum over the possible observation histories that we could have revealed. And then we say, okay, but actually, if we reveal these D-joint observations, it doesn't matter what we did before this. So I'm just going to sort of take this off. So I'm going to compute the new joint belief. Everything that happened before that, I'm going to ignore. I'm just going to focus on the parts of the policy that assume that I have observed this particular tau in the first D stages. So that's what this like phi constraint to tau means. It means that we only look at the observations that happen after this tau, which is of length D. Then we can, so that gives us the actions that we have beyond stage D. Okay, then here, we of course also reduce then the horizon to H minus D because we cut off the observations.
What is probability time? What does it mean?
It denotes the probability that the agents have received this particular observation tau under their policy. So, I mean, you can compute it as a huge conditional probability. It's, I mean, let's say that D is 1. then things are still simple. Then it's just the probability of, then this is just one joint observation. Then exactly this observation function tells us what it is, but actually also have to aggregate over the states. So we have some initial belief. We can sum over because of condition on the new states. And then we know the probability of this joint observation given that new state, and we know the probability of the new state given the old state and the action. If we do it for multiple, if d is larger than 1, then we have to also sort of keep conditioning on the intermediate states, and then we can compute this using the observation function and the action in the transition function and the policy. I can try to write this out.
They're saying that if the policy for the first d many steps are fixed, then you can compute it. Is that what you're saying?
Yes. So there, I think okay, we'll put this initially not on the slide, but there is a actually for using this formula, there is a condition that this phi, which represents the policy that has already been fixed, is specified for the first d stages. So that's what we're doing. So actually, when we use this heuristic, we are sort of gradually increasing d until we reach our d that we want. So that's this slide. So we define the stage of a partial policy as the smallest t such that phi is not defined on. I'm confused. I think it should be. So it's not defined for some. There exists a local observation history of length t such that phi is not defined, because this is an ambiguous way to write that. But so like initially the stage is 0. Then once you have specified all the actions that the agents take in the beginning, then the stage is at least 1, etc. And so to use this equation, the stage has to be at least d because it has to specify the action for these first d stages. And so to sort of fix that, we actually define the depth d heuristic as the heuristic that sort of increases the depth of the heuristic up to d, and then sort of if the stage is smaller, it's just a stage. And if the stage is 0, then actually the heuristic, I don't want to compute the heuristic because then it means it's too close to the root, and sort of I'm basically solving the same problem. So if the stage is 0, then I just set the heuristic to infinity. I'm going to expand all of the nodes, and then I have all of the I have to maximize over all the joint actions. Once I've expanded all the joint actions, then I can start using it. Also, there's another problem that fixing this problem sort of introduces a new problem. Because what you typically want is that your heuristic is decreasing in a star search, because your heuristic is sort of the best upper bound you want your heuristic to be the best upper bound you can give on all the nodes that are below it. Well, if I already had some heuristic value, now I'm going to consider a subset of this, then of course I'm at least going to give the same guarantee. And when I'm going to change the depth, that is no longer the case. So if I have a fixed depth, then it's fine because I defined it as a optimization problem over the extension of this partial policy. Well, I have a partial policy that specifies more actions. Then sort of the set of policies I'm optimizing over becomes smaller. So then indeed this value of the optimization problem becomes smaller. But if the depth changes because the stage of the policy changes when you increase it, heuristics with larger depths are looser because you reveal more information. So then suddenly you could accidentally increase your heuristic value. We don't want to do that, so we fix that by sort of taking the minimum with the heuristic value of the parent. So this is how we compute the heuristic technically. And then we have the determination. So that's really a bit of a mess to formalize. We just define this early determination on a search tree, which itself also has a particular heuristic. Right, so we again using the A star search to compute a heuristic, but in that nested A star search that computes a heuristic, we also need heuristics. So we need heuristics for the heuristic, right? Yeah, so that's this Q representing. That's the heuristic that I use to compute the heuristic. And I have some fixed policy phi for which I want to compute the heuristic. Like I said, I don't want to compute heuristics for policies that are of state 0, so that only maybe specify the initial action for some of the agents, because that's just too expensive, and I can basically do anything to make the problem simpler. So that's why we restrict to having at least stage 1. And also I want it to be an extension of the policy that I'm currently considering, because that's how I want to compute the heuristic. And now, I mean, in theory, in principle, that's of course not what the algorithm is doing, but if you want to reason about what this is doing, then you can just consider this fully sort of drowned out tree with all the heuristics filled in, and you can make a ordered list of all these heuristics. And then, what is this early termination heuristic? Well, it's just the nth value of this list. Except that actually you might have already found a fully specified policy before you reach the nth value. Well, then it's that value. So yeah, that's the details of the early termination. Then if you just keep this intuition in mind, that it's actually just the nth largest value in the search tree. Or if the star search is terminated earlier, then of course it's just the value of the star search that is star search fine.
I'm getting a little bit lost in the details, but could you? It's getting late in the day also, but could you just again say, like, intuitively, what should I? How should I think about this?
So this LM phi of Q,
yes,
is you want to compute a heuristic for policy phi. You fill your whole search tree with heuristic values according to heuristic value Q.
That is admissible and everything.
Yes. And then you take the nth largest value among all these values. That's the LM phi of Q. And I'm going to use that to define the early termination heuristic. Yeah, so there are some boundary cases, but the main thing is that we're sort of doing this like defining the QMD recursively, and in a sense it's a very similar formula to what we saw before. So we have this fix to make sure that it's actually decreasing when you make the policy larger, and then this is again this expansion over over all length the observation histories, except that maybe we need to fix this to make it smaller in the stage. And then here again we have this weighted sum, but before we had the actual values of these constraints, of these like lower horizon Dec-POMDPs, and now we don't put the values here of the lower we don't put the actual like optimal values, but we put this heuristic from the tree here. And then in the next stage, of course, this is going to be my heuristic. But yeah, I mean, this makes things quite. This is quite a challenge to properly formalize, and this is also not. Yeah, so how in practice, of course, you compute this nth largest value just by running the A star search for m steps and then just terminating once you have the m steps and then just returning the largest value. We don't have this whole list. Yeah, then there are a few more details. So you have this clustering, this incremental clustering that also works for small step search tree. So then instead of having in this tree, you had all the local observation histories of a particular agent, not all like of all the agents. Now you have clustered local observation histories of all the agents. We reuse the heuristics essentially by sort of storing them by initial belief and policy that we've I mean this partial policy that has been specified so far, and the clustering structure. That's also, of course, important because you have different clustering structures, then sort of the policies mean different things. There is a last stage optimization, because in the last stage, if you have the last stage for the last agent, then actually you can just compute that at that point is the optimal action. And okay, so we looked at arbitrary termination based on the number of iterations. What we can also do is say, okay, if we somehow know that the policy is quite bad, then we don't need to like compute a very good heuristic for it. Then we already know that it's, yeah, I mean, going to be somewhere very far away in the queue. So then we can stop the heuristic combination computation earlier, based on the value, saying, okay, this already has such a low value that we probably won't need to compute, like won't need to look at this node again. Then here is, okay, so to do the clustering, we need to work with the full joint distribution over the previous, well, either over the previous joint observation history, or actually in practice over the clustered observation history, so over the previous clusters of all the agents, the new joint observation and the state. We need to reason about all of these. How do we actually store these? Well, not as a full distribution over this, but it turns out that typically these conditional. So if we condition on the joint observations, then typically quite a lot of things become equivalent. Just the agents don't notice while the execution is happening. But the good thing is that if, like, many of these are equal and we only store an index, saying it's that conditional distribution, then yeah, I mean, the memory requirement becomes a lot lower, and also we can sort of reuse particular values. For example, we can just compute what is the expected reward if we take a certain action in this state, and we can also store that and reuse these values. So yeah, in the end, to make it more efficient, you really have to store a couple of things for every state. So of course, I mean, we have to store the policy, that's clear. And also when you have to, because we're doing clustering, you also need to store the clustering structure, that you need to know which clustered local observation history actually corresponds to which actual observation history. So these three together is also what the output of the algorithm is. It's sort of a clustered policy, and from that you could expand that to a full policy, depending on the whole observation history. But of course, I mean, if you have a large horizon, the clustering is very good, and that will be way bigger. Yeah, so and then you have this clustered joint observation history. If we condition that we have a particular state distribution, that's the distribution that I just told about, that we have to store because that we need to compute this reward, but actually we can sort of keep track of this reward that we don't need to recompute it every time. There's also a list of heuristic values corresponding to this policy, and there's sort of this depth is dynamically changing. We also store that corresponding to this policy. Then we know sort of which heuristic values are still up to date and which one might be outdated because they correspond to a lower depth that we don't update anymore. When we add a new action to a partial policy. So these were all the technical sort of details that I want to talk about, but I can just try to explain some things a bit more.
Thank you. Thank you first. So, yes, this was helpful. Are there any further questions or comments, or protests? I was also thinking about, like, in the context of certifying algorithms, how would you prove that this is correct?
Yeah, so I think that's a very interesting question, and there is maybe something that is helpful here, like for this final. Yeah, I mean, so this, because it's a relatively small tree, it doesn't show that well that you actually can leave out the whole part of the tree. So right. If you have all of these values, yeah, and you have sort of a certificate that these values are correct, then you know that your final answer is also correct. Mm-hmm. So this sort of the policy, the heuristic values that are on the frontier at the moment that you stop, those together do form a certificate of that you indeed found the optimum. And yeah, I mean, typically if you're so the number of nodes on this frontier is manageable. That's also, I would say, like actually one of the good things about the small step search tree, because there, I mean, so the number of nodes on the frontier is something like the outdegree times the number of nodes that you expanded, a little bit less typically, but around this order. Yeah, with the normal search tree, that's going to work. But the small step search tree, the number of things that are in your frontier is of a manageable order. So there could be something interesting in there. But then, of course, you also need to sort of certify that the heuristic values are correct, and that, I mean, might either lead you to, if you use this heuristic approach, then not heuristic. If you use a recursive approach, then that might still lead you into trouble, like with huge certificates. But if somehow the problem does have sort of this MDP computation is very easy, this dynamic programming. You sort of can agree that has been programmed correctly, or sort of, I mean, that someone can easily check that that's been programmed correctly. Then if they have all these values and they can just compute all those values, then there could be something in there. But I think there are many challenges to be addressed before we're there.
No, should be possible.
You think so?
No, like with the dynamic programming, proof logging, it's similar. It's going in the same direction.
Okay.
What we're doing.
Yeah, but this is for the MDP heuristic, right?
Yeah,
Just
but it's also like A star. It's also like
okay.
in some way you can think about like dynamic programming, or like the other way around.
Another thing I was just curious about is still getting back to these tigers. So in the decentralized setting, so if I understood correctly, you're saying like open the door every third step is sort of what you should do. Was sort of the situation, because sort of the most likely scenario is in fact that you hear correctly the same thing twice, and then you open the door and say a prayer, right? And likely you get the reward. But what do you do if you hear inconsistently?
So then you just listen again, but actually you can.
But should I do that? Because the other guy probably heard consistently, so we'll open the door and then the whole problem will reset, right?
Yes,
and then we're out of sync.
So you don't get, so sort of you just throw away these. Actually here, so in principle you wouldn't have to listen. You can also do a do nothing action, but the do nothing action is not in this problem. But I would actually, that makes it maybe a little bit unnatural. But actually
So is it what I guess? Is there an easy way of seeing what I should do? Is that if I hear inconsistently, then I should just sort of basically, I guess. Then I sort of would my guess be that, well, the other guy is probably going to open, so the problem resets. So I just do a no op for one round, and then I hope I will hear consistently next time.
Yes.
Sort of, is that the best I can do?
Yes.
Because I guess I sort of I should not, or should I wait, or no? But or is it better to? No, it's a 50-50 chance now. I've heard the tiger in both locations.
Yeah, so that's
and the tiger is so expensive that just
yes.
opening a door 50-50 is probably a very bad idea.
Yeah, that's very bad. Like even you even see that even if you have one sort of one observation which is obviously like consistent with itself, even then you don't want to open the door.
Yeah.
You want to have enough to have like two observations agree with each other. Only then you can risk it.
Okay.
And yeah, so but
but the fact that you want to do every third round, I guess this would depend on the 85%, right?
Yeah, not all the exactly right, of course, over here. So it's something like 20 if you open the like if both agents open the door to the threshold, it's 9 if only one of the agents opens the door to the threshold, and if they open the door to the tiger, it's -100. So
oh, sorry, say again. So this was the joint reward, isn't it?
Yeah, so if joint reward that together time to optimize, we didn't put the exact values.
So if one agent gets the tiger and the other one gets the money, then we don't get the reward. Or?
No, that's still -100.
Then it's still minus. So we only get the reward if
either we get the small, we get like half of the threshold if one of the agents opens the door, and we get the full threshold if one of them opens the door.
And we get nothing as soon as one of them lets out the tiger.
Yes, because then afterward you don't have time to take a trash.
Okay.
Yeah.
Ah.
Actually, it's better if they so it's better if they both open the door with a tiger. Then it's only -50. So there's, I mean, these values are just made up. Originally, there was like a POMDP benchmark, and then someone said, okay, I need Dec-POMDP benchmarks to make this benchmark. It's just sort of the classical problem that we're, yeah. So.
Unless you're saying this is not an industrial application. They do it in the zoos. Okay. Sorry.
Yeah, so but maybe one good thing to sort of break down what you said earlier. This heuristic, this optimal policy, sorry, you can actually represent that with a memory of size 2. So as long as the horizon is a multiple of 3, you can work with a memory of size 2, because I mean you only want to remember those two actions, then the program resets, or at least you assume that it resets. So here memory 2 is sufficient. Actually, if the horizon is 5, for example, then at some point you want to work with 4 observations, so then you need a memory of 4. But that's just for this one round where sort of you're using the extra 2 observations, and the rest you can also do.
You're saying I'm going to use 2 extra observations in one round, or am I going to do 2 rounds with 1 extra observation? Is that...
No, so you want both of your extra observations in the same round, and the reason for that is that with 3, if you have it 2, so divided 2, 1,
yeah,
that's still too dangerous because that's sort of the same as having 1, 0.
Okay.
But if you sort of actually having 1 more observation doesn't help you too much. Except of course so the only thing that it helps you with is that in the unlikely case that both of these observations were wrong, and you get an additional observation that's the right one, then it helps you because then you avoid the tiger.
Mm-hmm.
But that's pretty unlikely. Mm-hmm. But what you can do if you have 4 observations, then sort of a 3-to-1 majority is still enough of a majority to take the risk.
Okay.
So then it's less likely. I mean, this tie is not that unlikely, but having 3 observations actually having sort of a not having like an having the same observation every time becomes even less likely. But then when you have 4 observations, there are more cases in which you can open the door, because then you can also do it with a 3-to-1.
Interesting.
Yeah. And of course, yeah, right. If you change to 85, or if you change the rewards, then this might become longer.
Yeah.
Probably also become.
Yes.
I think it's an interesting question. Will the problem become harder or easier? I think for the solver it will become easier, because if you reset less often, then you can sort of cluster actually more. It's counterintuitive, but that's because you cannot prove that you can sort of cluster these things away that you reset, because it could still be that the program didn't reset and then it did give you information. You just don't know if this information is strong enough to actually use. If you would open and reset the program less often, then you can cluster more, because you can use this like sort of that the order of the observation doesn't matter as long as you didn't reset.
Okay, good. Thanks.